Welcome to the glass plate. In this exercise we're going to take a look at what happens with the flow that moves through a tube that is narrowing. Upstream of the narrowing at point 1 we have that the diameter d1 is 2 inch. Downstream at 2 the diameter is only 1 inch. Water is flowing in at a given flow rate of 10 liters per minute. And the pressure here 1.1 bar. And I would like to know what happens here. What is V2? What is P2? This tube is laying horizontal on the table, so potential energy effects can be neglected. It's all at the same height. Okay, let's try and find out. This is a steady state system, and thus we could take a look at what a mass balance says. Mass balance read the volume between 1 and 2 as 0 is in minus out plus 0 as you don't produce water. So the flow rate in, the mass flowing in, equals the mass flowing out. From the inflow, where I know the volume, I can compute the inflowing velocity. The flow rate is the cross-sectional area times the velocity. Thus, at 1, I have V1 equals the flow rate divided by the area of 1, giving me a velocity of a meter per second. V2 at position 2, here, one that I would like to know, can we compute it in a similar way? It is the volume flow there, but that's the same as the volume flow at point 1, which I learned from the steady state mass balance. Density of water doesn't change, so if the mass flows are the same, then the volume flows are the same. But obviously the area is reduced by a factor of 4, and thus the velocity goes up by a factor of 4. Okay, I've solved the first question, what is the velocity? Then now what's the pressure? Would it be higher? Or would it be lower? You could argue both ways. Let's see how we do this. In this system we assume that this narrowing is gradual, so that frictional effects are small and can be neglected. That means that we can use Bernoulli's equation between point 1 and 2. And that says that the inflowing mechanical energy must flow out. And in a steady state, that means that the half V1 squared plus G, Z1, the potential energy, plus P1 over rho equals the same, but then at point 2. So a half V2 squared plus GZ2 plus P2 over rho. Okay, let's scratch out a bit. These can go out because it's at the same height, there's no change. Z1 is Z2 if you want. I do know P1, V1, I computed also V2, so I can back out P2. P2, the pressure downstream, is the pressure upstream, and then I need to correct for velocity effect, in essence kinetic energy effect. So that's going to be plus a half rho V1 squared minus V2 squared. This is known, 1.1 bar, these I have computed, and realize this is smaller than 0 as V1, the upstream through the bigger part of the tube, is smaller than downstream through the narrowed tube. Thus, this is negative, hence P2 is smaller than P1, and if you put in the numbers you're going to get a drop towards 103 bar from the 1.1 bar. Okay, do realize that this drop has nothing to do with friction. The water is flowing through without any appreciable friction. We have neglected that. The pressure is changing because the velocity has gone up. The velocity has gone up, meaning that there is a switch over from less kinetic energy to more kinetic energy. And that energy has to come from somewhere. Nothing is adding energy to the system, so the water takes it from itself. It cannot take it from the height. All it can do is convert part of its pressure energy into kinetic energy. And thus it has less pressure energy left when it's flowing through the narrowing. Would be nice for yourself to think what happens if I gradually increase again to the final diameter. What will be the velocity then? What will be the pressure? If you do the analysis, you will find that the velocity will be back at 1 meter a second and that the pressure will recover completely to the original pressure if you neglect friction.